Yes, welcome you all for another presentation on electronic devices and circuits in our continuous presentation sessions. We are discussing about the transistor bias configurations, right? So, in the last presentation, if you recall, we have seen the one of the simplest and the first and the foremost important bias of transistor is nothing but the fixed bias that we have seen in the last presentation, right? We have seen the circuit diagram, how simple it is, and thereby we have seen how stable that fixed bias circuit is by evaluating the stability factor of that particular circuit. Clear? In today's presentation, I would like to explain you the second configuration, means in the transistor biasing methods, the second one is that is the collector to base bias, right? It is a collector to base bias configuration. This is something little bit improved version of the previous one, means it is improved version of fixed bias configuration. So how the circuit diagram of this collector to base bias looks like, right? So it is very simple circuit actually. In fact, I will draw the circuit for you. So this is simple using an NPN transistor. In the same as we have seen in the fixed bias, the emitter terminal is kept at zero potential, means this is your emitter, and however this is your collector and this is base. This we already know that. And here for this collector we are connecting the collector resistor RC. This is the resistor RC. Now this is your plus VCC actually. This is plus VCC, and here from the output, from the collector point, the output will be taken with respect to your emitter actually. So this is what V out, right? This is what the output actually. And whereas now the base resistance, so RB, so the base resistance RB is connected somewhere from here to this base point. It is connected to the base actually. Okay, now here the input is applied. This is, you can say it is coupling capacitor. This is also coupling capacitor, right? With respect to this emitter, between the base and an input, the input will be applied. This is V in actually. This is input. This is what your base resistance are also called as RB, base resistor RB, right? This is what a very simple circuit. Remember that between the base and the emitter there is a internal voltage will be there, V suffix BE, that is base to emitter voltage will be there internally, right? So if it is a silicon transistor, then the value of VBE is 0.7 volts. That is very important. That we will that will be considered during the solution part if any problem is given. So in that given problem, we will use the value of VBE as 0.7 volts for the silicon transistor, right? Now coming to this circuit diagram, this is a very simplest circuit for collector to base bias. What is collector to base bias? As per the name of this collector to base bias, the base resistor means the RB is connected from here collector terminal, from this collector terminal. So from this point it is connected to the base terminal. So between collector to base, the feedback resistor, it is connected like this. The base resistor is connected like this. That is why it is called as collector to base bias. Collector to base bias. Suppose if you compare this circuit with our previous one, that is the fixed bias, there this RB is directly connected to here plus VCC, right? So this RB is connected across this RC, both will be connected to common power supply, means plus VCC. But in this case, this RB is connected here at this point, right? Now, Now let us say that, so here through this base, the IB base current, IB will flows actually, the base current IB will flows, and then definitely from this collector, and through this collector the current IC will flows, collector current flows, emitter current obviously it will be in this direction only. Of course, we will not use this emitter current because the emitter is grounded here, therefore the emitter current is of no use. There is no purpose for this IE because the emitter terminal is grounded here, right? Now, so from this terminal, from this point, collector point, the current IC flows like this, it will flows like this IC, the flow of current will be like this, it comes in downward direction, and base current IB flows towards this. Now obviously through this RC, what is the current flows? What is the current flows? What is the I value here? Tell me. So this is node, let us say. Let us assume that this is the node, right? This is the node. From this node, assume that your IB is leaving. Your IB starts from this node and it flows like this. And again your IC is also leaving. Therefore, from this node, okay, IB is going like that and your IC is coming like this, means that from this node, these two currents going away. Then what is the incoming current? I is nothing but definitely IB plus IC according to your KCL. Therefore, this current must be, the current flows through this RC must be I is equal to, what is I? Here I is equal to IB plus IC according to your KCL. Because in fact, as we are connecting to plus VCC, we are connecting like this. Otherwise, this will be shown like this actually. So this VCC will be connected like this, and then the corresponding circuit will be connected like this. Or otherwise, this is the simplest way of representation, right? Therefore, what is the current flows through RC? It is the sum of base current and then collector current. That much current flows through this RC, I mean collector resistor, right? So this is the simple circuit. So therefore, you must remember in this circuit that your I, the I which flows through this RC is nothing but IB plus IC. This you must remember. This you must remember. Now, in the same way what we have seen in a fixed bias configuration, in this configuration also, let us apply the Kirchhoff voltage law at the input loop. Input loop is nothing but from plus VCC, you take the flow is like this, from plus VCC and then come to this towards RB and then come in this side, come to the base side and coming to this ground side. If you take the flow of the loop voltage, it will be like this, it will be like this, right? From this plus VCC, it comes to RB and again it, okay, and it comes in this direction. So this is what your input loop of the transistor. Clear? So now by applying KVL, right? By applying KVL, what we will get actually? By applying KVL, I will write the expression. By applying KVL at the input loop, you can write like that. By applying KVL at input side of the, at the input side of the transistor, by applying KVL, what you will get from this? Okay, if you apply the KVL, so this definitely VCC is equal to, from here VCC is equal to RC into I, means RC into I is nothing but, what is the I value? It is IB plus IC, means that what actually? RC into IB plus IC. Clear? VCC is equal to RC into IB plus IC, and come to this part, RB into IB plus RB into IB. Clear? RB into IB. Next what? Plus VBE, base emitter voltage, plus VBE. This is what the equation. Put in a box. Let us call this equation as number 1. Call this as equation 1. Or otherwise, simply you can mark it as equation number 1. Clear? This is what the KVL, Kirchhoff voltage law. Therefore, VCC is equal to I into RC, where I is equal to IB plus IC, and plus RB into IB plus, and the potential means the potential across RC, the potential across RB, and the potential between base temperature voltage. These three potentials, sum of these three potentials equal to your VCC. That is what the meaning, right? Now, from this expression, I need to find out the value of IB, right? So, for this, I just not required this circuit diagram, and I am erasing this because I want to bring out the relationship for IB, right? So, from that equation, you can write from this equation number 1, from equation number 1, you can write the expression for IB, or otherwise I can, once again I will write here, VCC is equal to what? RC into IB plus IC plus RB into IB plus VBE. This is what the expression, no? And even I can remove this part also, not required now, and I will simplify from this itself. And this implies, and further, here IB is there, here also IB is there. Now take IB as common here. If you take IB as common, definitely it is RB plus RC, is it not? So RC into IB, RB into IB. So in these two terms, IB is there, therefore IB take as RB plus RC, and plus what you will get, RC into IC, RC into IC plus VBE. Clear? This is what VCC is equal to. This implies further bring the relation for IB. Therefore, if you write the expression for IB, therefore IB is equal to what actually? VCC minus VBE, clear, minus IC into RC, means that I need for IB. Therefore, bring this RCIC plus VBE, these two terms to the left side. Therefore, they will become like this. So, minus sign will come. So, so I want IB, no? Therefore, by RB plus RC, you will get RB plus RC. This is what IB. This is what IB. This is what IB. This is what IB expression. Now, what I should do? So, you must recall your stability factor definition. What is the stability factor? Stability factor S is equal to, it is 1 plus beta by 1 minus beta into dou IB by dou IC. You must remember this. This is what the stability factor definition. 1 plus beta by 1 minus beta into dou IB by dou IC. Clear? Therefore, from this definition, I need to find out what is dou IB by dou IC, because beta is constant. Therefore, 1 plus beta, 1 minus beta is there, dou IB by dou IC. I need to find out this value actually, dou IB by dou IC. Therefore, what I need to do? For this IB value, you differentiate this IB with respect to IC. Therefore, you can call this expression as equation number 2. You can call this IB expression as expression number 2. Now, differentiate IB with respect to IC. Then this becomes, okay. So, I am erasing this also. Now, by differentiating the IB, means that what actually? So, now I am going to differentiate, means dou IB by dou IC. If you find, okay, here I will write, means dou IB by dou IC, or dou by dou IC of IB is equal to, what you will get actually? So, you differentiate this part dou, okay, with respect to IC, then VCC minus VB is constant, no? This VCC minus VB is the voltage difference. It is a constant by this RB plus RC. So, this entire part becomes 0, because differentiation with respect to IC, because it is a constant, therefore differentiation with respect to IC becomes 0. Then what you will remain? Because no IC term is there, therefore it is 0. Then minus IC into RC by RB plus RC. So, in this, as we have IC, Therefore, dou IB by dou IC means this becomes 1. Therefore, what you will get, minus RC by RB plus RC. RB plus RC. This is what you will get. Therefore, your dou IB by dou IC is nothing but this minus RC by RB plus RC. This is what your dou IB by dou IC. Now, substitute this value in our stability factor definition, right? Substitute that dou IB by dou IC value in that stability factor equation. Then what is stability factor? S is equal to, it is 1 plus beta by 1 minus beta into dou IB by dou IC. Clear? So, at this place, here, substitute this value. Dou IB by dou IC is nothing but this one, minus RC by RB plus RC. So, at this place, then substitute, then this becomes 1 plus beta by, what you will get here? 1 minus beta into, what is this? Dou IB by dou IC is nothing but minus RC by RB plus RC. Clear? So, here minus into minus plus, therefore, you will get plus, because minus into minus plus, therefore, this is what. Now, I will erase this part actually. So, okay, now I think, so finally, what is your answer? Therefore, your S is equal to, this much. Therefore, S is equal to, now this is the stability factor, 1 plus beta by 1 plus beta into RC by RB plus RC. This is the stability factor. This is the stability factor of collector to base bias circuit. Now, in this case, there is an assumption we have to consider. In this expression, if assume that your RC is very, very greater than RB, if one condition is that if RC is very, very greater than RB, means that what? RB is very, very less than, or otherwise RB is very, very less than RC. So, assume that the RB base resistance is very, very small compared to RC, then in this case, your RB plus RC is equal to, RB plus RC is approximately equal to RC, because RB is very, very small, then RB plus RC equal to RC. Therefore, here, in place of RB plus RC, if you put RC, then this RC will cancel out. Then what you will get, 1 plus beta by 1 plus beta. In this case, then what you will get? So, what you will get actually, if the base resistance is very, very small, then S is equal to, it is 1 plus beta by 1 plus beta. You will get. Then, both will be cancelled out. Your S value is 1. This is what? Compare this stability factor with your previous fixed bias one. This is for RB is very, very less than RC. This is the condition. This you must remember. If the okay, for this condition only it is 1. Otherwise, no. Therefore, while selecting the transistor circuit, or otherwise, while fixing the transistor circuit under, collector to base bias, we must choose the value of RB in such a way that that must be less than RC. Right? In order to connect the transistor in collector to base bias, the very important thing, the collector resistor must be very, very high compared to the base resistor, or the base resistor is very, very small compared to your collector resistor. Then only you will get your stability factor is equal to 1. So, whereas this is what the stability factor. Actually, what is the required value of the stability factor? What is the minimum value of the stability factor? It is 1. If the stability factor is 1, then you can say that that particular biasing circuit gives very, required output, proper output, or the desired output, you can say, right? So, if you compare this result with our fixed bias, in fixed bias, it is S is equal to 1 plus beta. In fixed bias, S is equal to 1 plus beta. So here beta value, we know that it varies from 50 to 200. Therefore, if you substitute here beta value as 50, 50 plus 151, that is much more greater than 1. That is why fixed bias is not preferable. Fixed bias is not at all preferable. No. So therefore, the collector to base bias is something improved version of this fixed bias. Okay, under this assumption you will get you will get there is a you will get the stability factor is 1. If the stability factor is 1, the circuit is more stable and it gives the stable output and gives the better output. Even it gives noise free output. The noise will be very less actually at the output, right? So this is the brief information about the collector to base bias configuration. I hope you understood this concept very well, and if so, don't forget to give your observations and comments, and even you can share this, and even you can like, and even you can subscribe also to this channel. And your valuable observations and comments and suggestions is highly I mean welcome and appreciated, and they will be considered for the improvement of the content of this channel, okay, in such a way so that the most of the students community will be benefited, okay. So they will get maximum benefit out of these presentations, right? So with this I will finish today's presentation, and we will meet in the subsequent presentation. In the coming presentation we will see the next type of biasing, and that is a very important one, that is the self bias, also called as emitter bias, also called as voltage divider bias, and also called as universal bias. There are many names for that. In fact, that is very important, even examination point of view, and even your GATE and UPSC IAS examination point of view also. That we will see in the next presentation, right? Till then, have a wonderful day.